Okay, well, welcome, folks. This is our lab for Design 330. It's Friday the 19th, and we're on a live meet on Google Meet. I'm going to do some demonstrations for you today on the area calculations, the Inventor properties for mass and volume, and then I'll take some questions. So we are recording right now. Let me know if you have any questions. Feel free to hop on with questions if you want. And we'll just, if it's okay with you, we'll just get going. I do also have an 11 o'clock production meeting. So here we go. All right. So the question that was asked for, and let me zoom in on this, was a quick demonstration for what I mean to put on your area data, which was the inlet filter open area, inlet check inside diameter area, and piston pressure area. So now what you're going to find when you do design is sometimes you just create numbers and you're not going to use them for any specific purpose right now, but somebody will ask you about them in the future. So there are just certain things that you always figure out. And areas and volumes are always needed somewhere along the design process. So if you've done it already, you're in good shape. So we're not going to do anything with these numbers. We're just going to get them and sort of have them available to us to work with. I will talk today a little bit about how you might use them in the future, but we're not going to do it now. So the first one is I just designed something called the inlet filter, and there's a bunch of holes. So one of the very first things I would do is find, well, how much area do those holes take up? Because if I'm sucking water in, sometimes somebody's going to want to know about how much area that water can flow through. You can imagine if it flows in through a very, very tiny area, it's going to be hard to suck the water in, sort of like a small straw, versus a lot of big holes would be like a big straw. And our piston pump is sucking water in, sort of like you're sucking in on a straw. So knowing what the numbers are may be useful at some point. Same with just knowing those check assemblies. Like, why did I go to a 1/2 inch pipe? Well, it turned out that when I tried the thing, the 1/4 inch pipe didn't work very well. So I went to a 1/2 inch pipe. And I found that out by experience. But a good project engineer probably would have been asking for information ahead of time to figure it out before they went to the trouble of building something. So just knowing some areas are good. And I absolutely know that piston areas are always used in calculation. And so we're going to figure out what the area is on the back side of the piston, and then I'll show you what we can do with it. So that's some of the area data. We've already figured out that we need to calculate the pump capacity and make sure that 1.5 inch stroke is enough. And maybe I want more, maybe I don't, but we're going to set and see, is a 1.5 inch stroke enough? And then these material volumes for manufactured parts. There's lots and lots of reasons why somebody would want to know the volume of material used. Now, some companies also, almost every company actually, wants to know what is the volume of the material that you used to make it, not just of the part when it was done, but the part before you even started. So if I made something out of a block of brass that was 2 by 3 by 2, I'd want to know that. But I also want to know what's the material of the volume that's left over when I'm done. And that's mostly so that we can figure out weights of things. Because weight can be a big cost when it comes to shipping. Weight is a big deal if I'm having to carry something underwater or in a drone or. So how much something weighs when it is done is an important piece of information. And I don't know what we're going to do with any of that data yet. I just know that in general, we find out about areas, we find out about volumes, and we find out about mass. Okay? Does that make sense to everybody? Is that sort of like, oh, okay, I get it. And so you don't have to do anything with these right now. You're just going to calculate. All right, so let's take a look. I just put them all on one calculation sheet, and I'll take snips of these. And remember, when I snip, if I want to see the little background grids, I can do that, or I can view it and turn them off, and then I only see the grids that I want to see. Okay, now I want to show you something else. Do I need to know the area down to the billionth of an inch? I don't think so. So I'm going to highlight these and say I just don't need to know that much. That's plenty. Okay. And so you can see that a small hole makes a really small area. But when I've got 20 holes, that's, maybe that's still pretty small. An eighth of a square inch. That's pretty small. That's sort of the size or a little bit smaller than a straw that you would get at Starbucks. And so if I go to a bigger hole, and I picked common drill sizes, okay? 3/32, 1/8, 3/16, 5/16, and a quarter. Sorry, this is 5/32, not 5/16, 5/32 and a quarter. So I picked some common drill sizes. I looked at my drawing and said, well, I think I can get 20 holes in there. What if I got 16 holes? Well, then I just got it there. That's why we use a spreadsheet, because I can change it really fast. And so I just want to see a spreadsheet like that. And what's my total area that the water is passing through to get from the river into my pump assembly? Okay. And I don't know if any of these numbers are good, bad, big, small. I know nothing about these numbers other than that I can make a valid calculation based on the hole diameter and how many holes there are. Okay, is that all going okay so far for everybody? The inlet filter, number of holes, that all look good? And if I need to, of course, then I would take my snip and I would have something I could put into my portfolio. Okay, so then I'm going to check my inlet pipe inside diameter, which you've already done. You've already done these calculations, so I just copied them. I just went to the one I already had, and I copied those, and then I just put in the area. And of course, remember the area is pi, and I don't know how to can I make that bigger? I can. Pi, 3.141 or 3.14 or 3.1, pi d squared, diameter squared, divided by 4. So that's all I did there. But you've done that calculation already. And so that's sort of like How big is the hole going into my check assembly? Now, I can, in my brain, reasonably think that somebody would want to compare this size with this size. Okay? If I'm going to be having an open area of a quarter of on a quarter-inch valve and pulling the water in that size, I would probably like to have at least that much on my filter, if not more. But certainly all of these have as much open area as that one at least. But when I go to my half-inch check, I see that its open area is 0.3. So I might, did you see how I used 0.13 holes? Because that's kind of close to that. Not all the way the size. Maybe I'd want to do that. Or maybe I'd want to go, I'd like to have 24. Oh, look at that. If I made 20, that's how somebody would use this. We're not going to. It's not part of our design process. But my job is to make sure that you understand that somebody's going to be doing this somewhere along the line. Okay, so inlet, check pipe inside diameter. And I don't need those to be quite so fancy either. There we go. 3 decimal places ought to be fine. Down to 1,000th of a square inch. Any questions on that part so far? So there's for my filter. There's for the area going into or out of the check assembly. And I'm just thinking somebody would probably compare these at some point. Okay, now we've got the pressure area on the back of the piston. Remember, somebody's pushing on the piston. And we're going to use air. So again, I took the back of the piston, which is the inside diameter of the pipe, and these are too big again. And look, these are the same. So I just copied the thing down. So that was the main thing I wanted to do. Okay, but then I wanted to show you how somebody might use that. And this is one way. So I know that the back of the piston where I can push with the air has a certain area, 0.302 square inches. Okay, and I know that I can have a little air tank up above in my next to me on the bank of the river, okay, with a long hose going out to the remote operated vehicle. And if I have a pressure regulator on that that's saying, okay, I'm going to push with 30 psi, 30 pounds per square inch. Well, if I've got 30 pounds per square inch, then if I multiply by how many square inches, I get how hard I'm pushing on the piston. So I'm going to push with 9 pounds if I use 30 psi, 18 if I use 60, and 27 if I use 90. If I use more than 90, I need special equipment and special waivers. 90 psi is the max that you can have on a commercial piece of equipment. You can get them that do 120, 150, 180 psi, but usually you have to have a special waiver and they cost a little bit more. So let's say I just go out and get like a paint sprayer. You can charge those things all the way up to 90 psi. Okay, but most of them try to work at 30. But this gives me some options. Okay, so let's see. I think mine has 0.302. So I can push, yep, piston load. So what this is area times pound per square inch. Okay, so area is square inch. Okay, actually, I'm going to do this on the Jamboard. I'm going to do it on a Jamboard. That's what Jamboards are for. This is a great one. Okay, so that right there, pounds per square inch, that's a pressure, PSI. PSI, pounds per square inch. And that's where the PSI comes from. Come on, click, there it goes. PSI, pounds per square inch. Okay, and so then I've got times square inch equals something. Well, I did this back in algebra, but I remember that if this is on the top and this is on the bottom, then I end up with pounds. Top cancels bottom. So there we go. And literally, this is how I learned it. Top cancels bottom. So whatever my numbers are, I just multiply them together and I end up with pounds. And that's how hard I push. This is how hard I push spread out over some area. And this is the actual area that I'm spreading it out over. And then that gives me my actual force. Isn't that cool? Don't you wish that they taught algebra that way? You know who taught algebra this way? Fibonacci. Okay, in 1170, he came back from North Africa where he learned algebra from a guy named Al-Khwarizmi, or I don't know how to say his name. But this is really cool. If you can remember this thing right here and top cancels bottom, man, you got it. Top cancels bottom. And I had the best math teacher in 7th grade. And it was very interesting. He had one eye, so he was always squinting at us because he only had one eye. And he taught us math with words. It was the greatest math class I ever taught. And it still sticks with me. He also taught us gazintas. Do you know how to do a gazinta? 3 gazinta 18 6 times. So we didn't do long division. We did gazintas. And we learned how to write them out. 3 gazinta 18 6 times. So anyway, that's how I'd teach math if I was a math teacher. I think it works better. Okay, there we go. Yeah. I wish everybody could have had Mr. Gillette for a math teacher. He was so awesome. So that's where that formula comes from. I do that all the time. Top cancels bottom. You want to learn everything you need to know about algebra? Here, I'm gonna teach you everything you need to know about A over B equals C. If you want to find A, put C on the top and go times. If you want to find B, put B on the top, put C on the bottom. There. That's algebra. That's all you need to know about algebra to do design. You need to know top cancels bottom and flip. Bottom goes on top, top goes on bottom. Now you know everything you need to know about algebra, too. Isn't it weird that they make you take like 8 years of math to learn that? So bizarre. Fibonacci taught 13-year-olds algebra in 3 weeks. And he first had to teach them numbers because they were used to X's and L's and V's and I's. So he had to teach them numbers, and then he taught them this. And in 3 weeks, he got students to start doing problems. Wow. Anyway, I digressed there. So that's the piston pressure on the back. Okay, and I look at that and I go, I wonder what pressure I might need, and I don't know. I guess it depends on how strong my spring is and how much it takes to push that O-ring. And I'll tell you, it's about 4 or 5 pounds because I measured it on the one I built. I had no clue what it would be otherwise. So I think this would work. 30 PSI would work, but I'd probably use 60 PSI because then it'll work strongly. And I'd stay away from this because, that's getting to be a fairly heavy pressure. Okay. Any other questions on that? That was a good question. Thank you for asking that one. I got to do my math thing. I love math. And this is what I know. Right? And okay, so I'm going to go on to another one. I'm going to tell you why I became a mechanical engineer. Because this was all I needed to learn. 3 letters, and see how closely that resembles that? I learned all of my engineering from Mr. Gillette in 7th grade. That's all I had to learn as a mechanical engineer. Even though they made it hard by doing calculus and all this other kind of stuff. I love mechanical engineering. That's it right there. Now, of course, figuring out what this is and figuring out what this is and figuring out what this is can be hard, but we have this wonderful invention called computer that helps us do it. It's great. Okay, pump capacity. We knew that we needed something, and so this is my cubic inch per. We've already been through this calculation of what we needed, but I'm just going, okay, if I've got a 1.5 inch stroke, how am I doing? And again, I'm going to make those a little bit less precise. And I think those should end up being in the middle. They are in the middle. These ones should end up being in the middle. So I just took that open area again. There it is again. And I multiplied it by 1.5. Now we get to the part, and I was supposed to have VMware open, and I don't. So I've got to get it. Excuse me for just a moment while it's coming on. And I'm just going to do one of the parts. I'll do the block housing maybe. It's going to take me a little while to come on. That's doing its thing. Oh, there it came. Came on. Come on, come back. Come back full size. Better redo that because I messed it up. There it goes. Okay. So let's see. I need to get a part. And I think I gave you some base designs, right? So let me go with that one. I don't know if this is the right one or not, but it'll work. Come on. Ah, should have opened Inventor first. See if I can get this to work. Sorry about this disruption. Normally I have everything up and running and it's easier to get to. So while we're waiting, does anybody have any questions? Okay. Now we're almost ready. See if I can do this right. Download that. Wow, that's just not doing its thing, is it? Let's put it on the desktop. And now I can open it. There we go. Okay, so here we go. I've got a base design, and you can see it's just a generic material. So I probably want to assign it. What did I say I was going to make this out of? Some sort of brass or cast brass. I think it was the yellow brass. So there we go. I've got a yellow brass part. And now if I look at my properties, so I went to the file, properties, and physical, it and update it. Let's just hit update. It tells me all sorts of stuff. And I'm sorry these are so small, but it tells me it's 2.3 pounds and a volume of 7.59 cubic inches. So I just look at this mass. Here's surface area, but there's my mass and my volume. And that's all I need to to do. Now, if I want to change the materials, I think I can just do it right in here. Let's say if I wanted it to be 6061. So it's got the same volume, of course, but now look, it's much lighter. And if I want to make it out of gold, probably going to be a little bit heavier. 5.9, 5.29 pound mass. Okay? So you can just come in here and get your volume and your we come back to the brass. Your mass and your volume. So Alex says, should you put them all on one sheet? I've done that here where I've got volume and then mass. And I'll just, so what was that? 7.9 was it? And the mass was 2.3, something like that. And then the filter is going to be PLA. And I'm not sure that you have PLA, but you could use ABS plastic and be just as, or an acetyl resin. Any of these three plastics would be just fine. Here's Peak. So that, yeah, ABS would be fine. If you wanted to say I'm going to make it out of ABS, okay, the pound mass. So yeah, you can just put that in here for your filter inlet. I think it was PLA, and your piston was 304. So you could put it all on one little chart here. Okay? And so there you go. That's how you do this set of sheets. And so I don't think it'll take too long. I've got them listed as half an hour to do these. I mean, you've already got them drawn. I don't think it'll take you a half an hour. Hopefully it'll take you like 10 or 15 minutes. This one I've got listed as half an hour. So I have like each of those listed as half an hour. And I'm hoping that those are pretty reasonable times for you. And you can arrange this as you wish. If you want to, you can put your Excel right down here, right on this one page, if you want to. You want to sort of get, okay, I've got hide those rows, make these a little bit smaller maybe, so that things just aren't quite so big. Hide those two rows. And then those were your, and then make this one not quite so big. Hide these two rows. And then maybe even put these like right here. What did I lose there? Oh, it's because I hid some rows. Maybe I don't want to hide those rows. Why won't it let me unhide the rows, you guys? There you go. I just needed to pull on that. That was really weird. So I can hide the rows later if I want to. So there we go. So if you want to, you can put everything on here. Maybe take one snip. Put it right on there. Up to you, right? You can put the, oh, I don't have my piston pressure area on here. So maybe you want another page for these, or maybe you want them all on this one page and you can rearrange it. Kind of up to you how you want to do it. Okay. All right. So there we go. Any other, so that was your watch demonstration. I'm going to turn the recording off.